Okay, it's time to do some robotics now. Our next speaker, Katherine Scott, comes from United States. She specializes in computer vision, robotic applications, and machine learning. She's the co-founder and software lead at PyWaw Automation. Katherine will do a brief introduction into robotics in Python. Please welcome Katherine Scott.
Dzień dobry. Hi guys. So I'm here from San Francisco. I brought a toy robot with me, and I'm here to talk about robotics and Python. So it's all in the notebook. So if this doesn't look like totally polished, it's because the notebook's getting better. But they're really awesome, so everyone should use them as a teaching tool. Okay, so overview. What do I do all day? I basically write software at a robotics company all day, day in, day out. And so I have to train people to learn how to use robots, how to write software for robots. So I wanted to build a tutorial that kind of covered some of the stuff that I do day in, day out. Day in, day out, I use basically a robotic software package called ROS. That stands for Robot Operating System. It's been around for 7 or 8 years. It's completely open source, and it is wonderful. And it's a lot of Python, surprisingly. So I wanted to come and talk about it. So I'm going to cover ROS. I'm going to cover the hardware I have here. It's actually pretty basic. There's not a lot of hardware fanciness going on. And then I'm going to talk about the software, and that's where the fanciness comes in. And what I've done is I have 7 lessons, and it sort of goes through getting progressively more and more interesting and progressively more and more, I don't want to say difficult, but more interesting at least. So why should you listen to me? I've been doing this, actually, as of last month, I've been a professional software engineer for 10 years, and most of those years have been doing robotics work or computer vision work or simulation work. So I started out in college doing legged robotics, moved on and worked for a mom and pop defense contractor in the States, did a whole lot of cool projects there. I also have coached robotics teams. My job prior to this one is I was actually building a mapping car that used FLIR cameras to do thermal analysis of buildings to figure out which buildings release too much heat and need to be better insulated. And so now, in the past couple years, I actually went and started my own company, my own robotics company called PyWaw Automation. And we build this robot. It's called a pick-and-place machine. And a pick-and-place machine's job is to build circuit boards. There's robots like this that exist already, but I wanted to build something completely different than what was out there. And the machines that are out there right now are really slow to set up. They're really good at making like 1 million boards, but to get to making 1 million of something, it takes like 2 or 3 days to set up. And I wanted something that was set up in a couple hours. So this gives you an idea of what my problem is. There are a bunch, that's an American dime, so it's like a very tiny coin. There's a bunch of parts over there. And when you build circuit boards, you have to take all those little parts over there and put them on your circuit board. And they're almost to the point where they're so small people can't do it. You actually have to have a machine to do it. So I can describe it or I can show it to you. And it basically looks like this. So I'm not going to play this whole thing, but this is what my robot does all day. And this is all almost entirely written in Python. And so its job is to come over, find all these little parts, pick them up, put them on circuit boards, and do it all basically automatically. So there's a thing. And wait for it, and I'll show you the setup here. So you just put stuff in, put parts in, and it goes around and basically figures out where everything is automatically and puts it all together for you. So before I talk about robots, I want to talk about the web, because I get people come in and say, oh man, I'd really like to work on robots, but you know, I've just been doing web dev stuff forever, and I don't even know how to start. And they really want to go, and they really want to go build robots, but they're like, all I know are these Python web frameworks, and so I want to build everything from scratch. Or I don't know that there's other stuff out there that's really awesome, so I want to build it all from scratch. And it turns out, like, you don't actually have to reinvent the wheel for robotics. There's actually, like, the best robotics package as it exists right now uses Python almost exclusively, along with some C++. And so you wouldn't write something like Django from first principles, so why would you write a robotics framework from first principles? And so this robotics framework is called ROS. And it is exceptionally awesome. It runs some of the most sophisticated robots out there, like some of these vehicles, like self-driving vehicles that you see. Baxter, you know, this really smart arm robot that people are using in factories, they all run ROS. ROS runs primarily on Linux, mainly on an x86 architecture, but there's now a lot of stuff to get it running on ARM. It is a really, really wonderful FOSS community. It is very much like Python, where all the people are exceptionally helpful, exceptionally awesome, and a lot of the work is out there free and open source. And it's also reasonably mature and battle hardened. It's 7 years old, so people have been using it for a while. A lot of the little bugs have been sort of pushed out. And probably the most interesting part of all of this is that it uses Python. You can use Python, but it can talk in Java, it can talk Lisp, it can talk C++, and it can talk JavaScript. And basically, you can take all of these languages and smush them together and use them in your robot. And a lot of times, you don't even have to know how the JavaScript implementation or the C implementation works. You can just use it, which is really great as a force multiplier. So what is it really? So like if you come from a web background, ROS, a good way to think about it is that it is your package manager, which is mainly through apt. You can also use Git. It is your build system, which in ROS is called Catkin. And it's your deployment system. So it uses a system it uses these launch files, which are basically deployment scripts. And it's all baked into ROS. The other way I like to describe ROS is a giant unified bus, or system bus. So when you have a car, there's basically an internal network in the car, kind of like Ethernet. That's called a bus. And basically, it's a simpler form of the internet. You just sort of talk on one channel, and somebody else listens on that channel. And you send messages across this bus. On top of all this bus stuff, all this pub sub stuff, there's also just about every utility you could ever think. So there's utilities for logging, there's utilities for rendering your robot, there are utilities for parsing config files. There's all those little tools in a very Linux fashion that you would ever want to use are all baked into ROS. There is effectively a plugin framework where you can kind of build modules, they're called nodes, and just add them right to a system. And finally, there's some standard libraries for handling stuff that you want to use in robotics all the time, like images and transforms and 3D models and all of these things. Oops. So, okay, enough lecturing. You guys want to write code? I'd hope you want to write code. So up here, I have this guy. I call this guy Twitchy. I picked up Twitchy on Amazon. He wasn't that expensive. And Twitchy is very much like this robot over here. This is a KUKA palletizing arm. And so this robot actually has a job. This does something every day, day in and out. And it sits at a factory, and it grabs piles of stuff and puts it on pallets. And so those pallets can go into containers, and they can get shipped out. And it's a really boring job, but this robot does it really, really well. And this little tiny robot here has the same dynamics as this large robot. So it's a really good teaching tool for something that's very practical. So I bought this guy on Amazon, but last week I was at Bay Area Maker Faire. There are actually now some people working on a really cool open source version of this. So if you guys want to build one of these and you have access to a laser cutter or a mill, this UFactory website actually has all the open source designs for this. So if you want to go build one of these, it's totally doable. All right, so you guys want to make it move around? All right, yeah, let's do it. So what's running Twitchy here is, this is just a regular, everyday, vanilla Arduino, and I did that, you know, you could use a Raspberry Pi, or you could use whatever hardware you want. I did that because I just had an Arduino laying around. A lot of people have them laying around. And there's nothing really fancy on here. It's just a shield, and there's a few pins here that basically move out to these servos, and then there's some extra power, because between this USB drive, you just can't deliver enough power to run all the servos. So all I do is I move the power from here into these wires, and then I use a control coming up from the Arduino. It's super simple. Oh, and there's a kill switch, because when you work with robots, you don't want to have an uprising, so you have to have a kill switch. Well, and actually, your robot can go do crazy stuff and hurt people, so you always have a kill switch. That's the real reason. All right, so let's talk about what I did to get here with ROS. So this is all up on GitHub. You can go run this at home. All it is like sudo apt-get ROS on Ubuntu, just 14.4 vanilla. A couple of other commands: set up your Katkin workspace, download the Arduino IDE, you know, and source a bash file. That's it. Or like you really could do it in about 20 minutes at most. All right. So once you do all that, how do you get this thing to start to move? So first thing we're going to do is we're just going to get this thing to move around a little bit by sending it messages. So we're going to write a ROS node that runs on the Arduino here, and this node basically listens on two channel, or it listens on a channel, or it subscribes to a channel, and then it basically publishes two other topics, which are like where I am as a series of 4 integers and where I am as a string. So what's going to happen here is I'm going to run ROS on my laptop. Laptop's going to send messages over, and it's going to say, here's a message with 4 integers that basically mean these 4 motors that are on the robot. Those 4 motors will move around based on those messages in the Arduino, and it'll echo back saying, hey, I'm here. Hey, I'm here. All right. So to do this, we do have to write a little tiny bit of C. I apologize. It'll be edifying. It's good. So to do this, what you do is you basically run this ROS. You just import a ROS header file. You import a servo header file. You get a couple of basically built-in ROS message types, and these are free out of ROS. You're just saying, oh, multi-dimensional array, cool. You do some C definitions here to say like, hey, I'm going to have this node. It's going to be running on this thing. And then we're going to basically have these state variables. And then you tell ROS, I'm going to publish these 2 things, basically state. That's the 4 integers that say where I am. And then you're also going to publish the status message, which is just a string. And I go in, create my servos. These are just super easy Arduino stuff. So this is where things start getting interesting. So when I get a message from ROS, it says, here's your 4 integers. All I do is I copy them to a local variable, and I write them to my servos. So ROS will say, put all your servos at 90 degrees. And the Arduino will say, OK, cool. And then it'll echo it back. Then I basically create the subscriber. This is listening on a topic called robot. So the thing where the 4 integers come in has a name, and it's a topic called robot. And when you publish to that robot thing, ROS is always listening there. And finally, what you do is you attach your servos to where they are on the pins on the Arduino. You give them an initial state. So right here, we just set them all to 90. We set up some hardware stuff. It basically says, hey, ROS, we're communicating over this USB at a baud of 115,200. We start our ROS node. We subscribe to our robot topic. We advertise that we're publishing to our state and status topics. And we enter our main loop. And all this main loop is here is get the latest data, copy it over, put the output screen, and publish it. And then spin once, which means basically listen. So hopefully that's reasonably clear. So we're listening on this robot topic. 4 integers come in. We're publishing a status message, and 4 integers come out of what we did. So to run this on ROS, once you load the Arduino, you need to set up a launch file. And the launch file is basically what tells ROS to say, hey, when I want to run this robot, you need to run this thing. So the ROS launch file will spin up what's called the ROS core, which is basically the big overarching ROS subsystem. And that's the thing that will bring your nodes up and down. It's important to note when you do this, node launch order is not guaranteed. So you just spin everything up, and it has to figure out what its spin up order is. Inside of these launch files, there's some other cool stuff you can do. So you can actually set system parameters. So if I had like some speed variable or something like that, I could put that in there. I can also pull in other launch variables, or other launch files, which allows you to build like big hierarchical robots like a Baxter. So all of this looks like this, and it's all in XML. And you can read this, it's super simple. It just says, hey ROS, there's a thing talking serial, its name is use serial node.py, and use this Arduino serial package. I set the port, which is where this thing is connected, and I set the baud rate. So this is all good. The robot's going to sit there and listen on this topic, but we don't have any way to send it messages. So we have to write a little bit of Python to send it messages. So here is a very short little Python program that will basically listen for, or basically spin up ROS, or spin up with ROS, connect to the ROS core, and publish those 4 integers. And what it actually does here is it goes through and just moves the robot a little bit. So it basically says, for one joint here, just this joint down here, just go ch-ch-ch-ch-ch, and then spit out a message. All right, so that's really basic. Let's take a look at it. So I'm going to send my Arduino. There it goes. And so all I have to do is run my launch file. And then I can run my little Python program to send it messages. So okay, not really. Oh, come on. That's not really exciting. That is not. This is really boring, actually. You're not gonna sit around and do this all day. Like, who wants to drive a robot by writing code? No one wants to drive a robot by writing code. What you want to do to drive a robot is use one of these, right? Like, for real. So why don't we hook it up? And the cool thing about ROS, and this is where things get interesting, is it takes about 10 minutes to hook this up. So ROS has a package for running controllers like this. It's called Joy, and they speak a standard Joy message. And so this thing, there's basically a ROS node listening at the other end of this USB. Here's what the USB is saying, and it just publishes this message called Joy, and it's got all the buttons enumerated. And all you have to do to hook this up is write a little node that listens to this thing and spits out the messages that correspond to your robot. So let's take a look at this. So here is another ROS node, and I call this, what is this, joystick driver? Joystick node. Here we go. So what does this do? Basically, I import the sensor message, these joystick messages, import the messages that Twitchy's speaking over here, and then I create a little class called joystick node. And it's the same thing again. We're going to publish to the robot topic, which is what Twitchy's listening to. And then we're also going to subscribe to Twitchy's state variable, which is just the output of Twitchy when it echoes. And we're going to subscribe to listening to this thing. And so inside of this, what goes on is that basically there's a state variable. And every time you get a new message, you look at the state, and you get the motor positions. And then you come down here and you look for what buttons have pressed. So basically, this is the input Joy message right here. Oops. Oh no. It's still rendering. So you get these input Joy messages, and if the button's been pressed a certain way, you basically increment where the motor is. So if I push up here, I basically take the thing that's going to get sent to Twitchy, and I decrement it or increment it. Then I do some really quick math here. That's a little list comprehension where I clip the values so they don't go too high or too low. I do a quick list comp to make sure that like something's changing. Like if I'm not pushing anything on the controller, I shouldn't tell Twitchy to move. And then if there is a change, I just publish it out on the topic that Twitchy's listening on. And then there's some stuff to, when Twitchy shuts down, to set it to a normal position. Okay, so that's the code. So all we have to do is write a launch file now, which is to say, like, all I need to say is that I have this thing, the thing that I just wrote, and I need to connect the two. So that looks like this. Basically, there's a new node in here. It's called Joy. And I say, there's a joystick. It's on dev input joystick 0. It has a dead zone, and it updates at a certain rate. Here's the thing that we wrote before, the thing that Twitchy runs. And then here's the little controller node that I just ran. So all I say is run this Python node and call it controller. So let's take a look at this. So I use this ROS launch command and give it, oops, wrong one. And so now I can do stuff like this, right? Hey, we got a controller. Sweet. So now that we have a controller, and I can move this thing around, what should we do next? Well, so when you build big robots, you know, like that KUKA robot I showed earlier, the way that you train those things, they're not actually that smart. You actually have something just like this, except they don't call it a joystick. They call it a pendant, which is this sort of pedantic big robot name for it, because they're big toys. And so what you do with that robot when you're running pallets a lot of the times is you just say, all I need you to do is go over here, grab this thing, move it up over here, and put it over here. And you just teach it each of these little motions. Basically, you have a joystick. You're like moving it around, click, move it around, click. So why don't we teach Twitchy to do that really quickly? And so the way we do this in ROS is that there's two primitives on top of this publish-subscribe model. There's something called services, which are little tiny, quick calls to do something, and then there's something called actions. And so actions are, the way I like to think of them, are if you were the Mars rover, right, and you want to say, I want you to go over there, the action would be, okay, I'm going to go over there, and I'm going to send you updates as I keep trying to get over there, and finally when I reach the goal where you told me to go, I'm going to give you a response and say, I made it, or I didn't make it. And so these all use the same ROS message generator. Okay, so what we're going to do is we're going to basically wire this thing up so that if I move the robot around and I click one button, the robot will sit at a position or record that position to a text file. And if I push this button, the robot will go to replay all the positions I just told it to go to. To do this, we'll have to do some modifications of a CMake file. It's actually pretty easy. It's pretty boilerplate. And then we'll have to run a package called catkin. And we also have to write files to describe what we want to do. So to make the robot just basically record a position, I'm going to create what's called waypoint.serve. And all this file is basically YAML. And you just say, I have a string, that's the file I want to save a point to, and I want you just to echo back that you did it. To replay all these motions, I'm going to build a file called build a play animation action file. And so what this looks like is that I tell it there's a file named replay, a step size, which is basically how long to run each step. When you complete running, you send me a result. And then as you're doing each step, you tell me what you're going to do. All right, so let's take a look at this. So this is what I'm calling armcontroller.py, and so this is the thing that will run that service and that action. To do this, we need to import actionlib, and we also need to import the service and the action messages that we just wrote. And ROS takes care of all of this. So if I write this service and this action message up here, and I tell ROS where they are, ROS will basically make the Python type that I need to use to send these messages over the ROS bus. So let's take a look at this. So I just create a little ARM controller class. I set a path to where I want to save all my files. I'm just going to save them to the desktop because I'm lazy. I'm going to create my service. So this is what ROS is basically, it's called a service proxy. And all it does is say, when you hear something, a service request on this topic, you send it here. And then you subscribe over here. So what ends up happening here is that whenever I hear a service message, it says, save it to file. And I go through and I save the position of all the joints to file. And then when I actually go to want to replay the animation, I just load it in and go through all those actions by sending out the messages to here. So let's take a look at this. Oh, and I also have to go do a little bit of bookkeeping here to take and add the waypoints to here and here, which is just basically adding additional keys like I did before. And so all I do to get this up and running is I add an additional add this new ARM controller to my launch file, and that's ready to go. So let's take a look at this. All right, so what I can do here is if I go like this, And so now I should be able to replay what I just did. All right, so we now have a reasonably working robot. So now we should add some smarts to it really quick. Oh, I got break for robot cool stuff. I'm not going to show any of this, but if you want, these are all the JavaScript libraries for ROS. So you can actually take all of this and actually put it as a web front end. So down the line, once you get your robot running, you can actually do some pretty cool stuff with it. So I'm going to do one quick example. I'm actually going to skip over this because I think I'm running pretty close on time. So that's basically basic camera stuff. But I want to get to the more advanced camera stuff. So ROS actually has this ability to understand what a robot's geometry looks like. And so you can actually teach a robot about its geometry and where everything is and use that information as you're running. So we do that using what's called a universal robot description format. And it's just basically a bunch of fancy XML where I articulate where the joints are and where the links are in this robot. And you can do this manually or you can export from your CAD program. And so all you have to do is build this RDIF file, either by exporting it or by hand. In this case, I did it by hand because I didn't have the actual CAD. But all it is it's saying, oh, there's the thing here, it's this big, there's a thing this big, there's a thing, a rotation axis here. And you can load this into your robot. And you can actually map the joint positions that are coming out of here into this thing, so you can actually render it. And you do this by adding a couple more lines to your launch file. And that ends up looking like this. All right, so now, oops, I have a little model of my robot. So I can actually do stuff with it in simulation. And I can actually take a look at some of its camera data. And I'm actually able to pull all of this joint information out and play with it programmatically. And this starts getting really, really interesting. Because what you can start doing here is you can wire it up with your camera. So the robot can start to figure out where it is. So now we're closing the loop. We now have this robot, and we also know that we can actually add into the robot where this camera points to. So the way we do that is we're going to use a package in ROS that is free to use, and we basically can use these AR markers to look for position. And this is all free. And all I have to know is that this is here. So these markers, these AR markers, are just little sort of QR barcodes. And they show the position of using these, you can actually look at the camera, know the position of the robot from the camera, or know the position of this from the camera, and then map where the robot is with respect to this so I can actually know where this robot is completely in world space. And in ROS, this is completely free. And all you have to do is create a small little file that says, hey, I have these 3 markers, and that they are located at these different positions. So why don't we take a look at this? And hopefully this works. This wasn't quite working earlier. But it's because of these extremely hot stage lights. So if I pull this up, what I can see here is, so this is the projection of that little robot model into the view of the camera using this AR marker. So if you can see here, kind of, you can actually see the overlay of Twitchy, its 3D model into the world space. So this is getting pretty interesting, right? So now the robot actually knows where it is, and it can actually reason about itself in that space. So Twitchy's got a couple of little dynamics things here because of the way the arm is shaped that don't quite line up. But this is getting pretty interesting. And what's even more interesting is you can see here, I'm actually getting a couple of these other markers here. Well, sometimes. So ROS actually has built-in utilities called TF. And so what TF will allow me to do is I can actually, using Python, ask the robot or ask ROS, hey, I know where my robot is because I know where this thing is. And I know where this thing is because the camera can see it. Tell me what the difference in position from this thing right here all the way over to this thing over here is, and you get that for free. That's a lot of math. That's a lot of linear algebra that you just get for free in ROS. So I don't know if this will come up completely. But you can actually run a ROS command like this. And there's a Python equivalent of it. Well, I didn't see it, but normally you'll actually get an XYZ vector and a pitch-yaw, XYZ position and a pitch-yaw roll vector that actually relate this position over here all the way over to this. So you can see where you could start building this up into something that's fairly sophisticated fairly quickly. So I think I'm pretty close on time here, correct? All right, so the last little bit here to sort of wrap up and show you where you go with this is that once you get the basics down, there's actually packages, Python packages in ROS that do inverse kinematic handling. So what I can do is I can actually use these inverse kinematic handling packages to say, robot, you know that this thing is over here. Figure out how to get all these joint angles that will actually allow you to move yourself all the way to here to pick something up. And so that's basically how you start building an interesting, real working robot in Python quickly. So I'm pretty much over time, but I think I can take maybe one question really quick.
Yep, and I'll just add that if someone asks a question, then he will get the conference T-shirt. So
Oh.
go on with the questions.
Katherine, quick question. The robot, does it know where it is, absolute space or relative space? So, like if you were to move right now, the arm, would it then tell the computer where it is, or does it only track its position relative from where you told it to go?
It actually, it knows where it is. So the Arduino is actually keeping track. So these are steppers. So the caveat, or not steppers, these are hobby servos. So the caveat here is at the level of hobby servos knowing where they're at, this thing right here is actually publishing the position of each of those hobby servos at probably 10 hertz.
So even if you were to pull the arm, it would know its updated position?
Well, they're hobby servos, so they're not going to move. So if you had like a compliant stepper or something like that, you would, you know, or you had an encoder on there, you would know. So it depends on what motors you use and what sort of encoders you use.
Very cool stuff, thank you.
Yeah.
Okay, so thank you very much for the great presentation and for the ROS demo.
Good.